This lecture recording is for the 13th of March 2019. This is class number 9 of Hydrology and Drainage Control. Before we begin the lecture, which is covering the NRCS Rainfall-Runoff model, let's go over a couple of announcements. First of all, the homework assignment that goes along with this topic is due next week, so please upload it to MU Online before our 4 p.m. class starting time next Wednesday. And then regarding that class next Wednesday, we're going to have a special visitor coming from the U.S. Army Corps of Engineers. He's going to be talking about some of the work that he's done with HEC-RAS and stormwater flood inundation mapping. So I think that's going to be a really exciting presentation. So please be sure to be there and on time on Wednesday, the 20th of March. We'll be live and in person for that class meeting. So like I already mentioned, today's lecture is covering the NRCS Rainfall-Runoff model. I get into the beginning of this lecture kind of the big ideas and the context that this material falls under. We're kind of transitioning in the course, whereas previously we've already talked about a lot of fundamental principles having to do with precipitation, evaporation, infiltration. Now we're transitioning more to some of the tools that a hydrologist can use to estimate the flow rates that occur during a storm, and that's kind of the information that a hydraulic designer would need to size infrastructure like culverts and pipes and channels and so on. So as always, if you have any questions on the material, I'd invite you to stop by during my office hours or just shoot me an email and I'll do my best to respond.
Before we talk about the NRCS approach, the big question of this course, what's the thing that the hydrologist has to say to the hydraulic engineer? How much runoff, right. So how much runoff, and then also when is the runoff going to be? So when we say the amount of runoff, we're not just talking about the volume, but we're also talking about the timing of it. And the timing becomes especially important for storage, for things like flow equalization basins, for storage like ponds. The timing is less important for culverts. Culverts are sized really just for the peak flow rate that's going to be going through them. So the way that I put it, if I was going to distill this course down to like one question that you're learning all of these fundamentals to be able to answer, it's for an area of interest, what are the runoff characteristics? So characteristics get into the amount, the timing, and then also some of the quality issues as well, because the characteristics could be talking about the amount of sediment that's being scoured out of a watershed, could be talking about the nutrient loads, things like phosphorus and nitrogen that are going to be stimulating algae growth in both rivers and like in the Gulf of Mexico. So those characteristics can have a lot of important factors that are all-encompassing. And so if we want to know what are the runoff characteristics, we have to have a description of the rainfall that the area of interest is going to encounter. And some of the data that we need to know about the rainfall would be the return period amount relationship. And so we're talking about 2-year storm, 5-year storm, 10-year storm. And so that's just for a certain probability of occurrence in a given year, how much are you going to see? Now the temporal distribution, remember that there are variations depending on where you live in the country. People who live in the Pacific Northwest experience kind of slow drizzle, might be a way to describe it, where the intensity is less of a peak than here in the Midwest, where we have the type 2 storm characteristics that are typified by that classic afternoon thunderstorm where the warm air rises very suddenly, then it begins to cool, the condensation occurs, and then there's a sudden thunderstorm. So temporal distribution is talking about the amount over time, and then spatial distribution is how much it varies over space. And we talked about how different basin sizes can affect the intensity of storm that you're expecting to see over that wide of an area. For instance, over the entire Ohio River Basin, if we had a table that was showing the probable maximum precipitation for gradually increasing watershed areas. And for a really big watershed, it's unlikely that you're going to have storms over the entire thing, really intense storms over the entire thing. And so the probable maximum precipitation for a large area is smaller than the probable maximum precipitation for a relatively smaller watershed. And that's just because a really intense concentrated storm can only occur over a smaller area. So spatial distribution is another way that we want to have all this input data that's going to allow us to answer this question: what does the runoff look like? So the NRCS method is going to use rainfall as one of the inputs. I'm sure you've heard of the word algorithm, and I always kind of cringe when I hear somebody say algorithm, because usually the people saying the word algorithm don't create algorithms. They don't really know what they are. It's just kind of like a buzzword that makes people think, oh, this is like important technical stuff. But the NRCS method is using lots of different inputs to describe an output, and rainfall is one of those important ones. NRCS method also somehow takes into account abstractions, although it's not very sophisticated in the way that it does it. There are other approaches that handle abstractions with more resolution. And so the abstractions that I listed here on the whiteboard as being one of the differences between rainfall excess and rainfall includes evaporation, interception, the wetting of surfaces before the water starts to move overland. And so the rate of evaporation during a storm event is going to be relatively low, because if you think about the time scale, evaporation is measured in terms of millimeters over the course of a day. And you looked at evaporation data from New Mexico, and you'll remember that when you looked at that, that was in the order of maybe, I think, 4 millimeters per day of evaporation, maybe a bit higher if you have a really low humidity and lots of wind. But a big peak storm that's dumping a lot of water, it can be several inches. And so we're talking now about maybe 10 centimeters or 15 centimeters during a really significant storm event. And so if you have 15 centimeters of rainfall, the amount of evaporation that occurs, even if it is that 6 or 10 millimeters of evaporation, is going to be relatively small. And so a lot of models just ignore evaporation, because over the long term it's a very significant factor in a water balance, but over the design of infrastructure term, even the course of a couple of days for the sizing of a pond, evaporation would be a minor factor. Interception can sometimes also likewise be overwhelmed. The amount of interception that you're going to see for a 15 centimeter storm event is going to be essentially negligible. Infiltration, though, is pretty important, and every model takes infiltration into account, even the rational method. When Darren was here in class last time, he mentioned that the rational method is one of the 3 approaches they're using for modeling. He mentioned the rational method, TR55. He said that they use some USGS empirical equations, and we'll learn about that in a couple of weeks. And so the rational method says that there's some C value, and all of the losses are lumped into that C value. But if you look at a table of C values, the main factor that it accounts for is differences in soil type and land use. Those tables are saying, you know, a grass surface versus a pavement surface, or roof area versus crops of some sort. And sometimes they'll have slopes built into those C value tables. Sometimes they'll get to the soil type that the different crops are planted on. But in the rational method, soil type, land use, and then this antecedent moisture condition is talking about the prior rainfall events before the one of interest. And so infiltration is really strongly affected by that. So on the left, these are the things that go into the model. You can think of this as the raw data that you have to go and gather for a watershed before you're able to do any kind of prediction on what the runoff characteristics are. And once you have that raw data, then you use some sort of a modeling to equate rainfall to runoff. And so There may be ways to estimate the rainfall excess by quantifying the difference between rainfall abstractions and infiltration. And then the shape of the hydrograph comes from either a unit hydrograph, or it comes from like observed unit hydrograph data or synthetic unit hydrograph data, or just typical patterns. And I showed you the typical rainfall patterns, and I mentioned type 2 just a moment ago. There were these curves that looked like this. The storm started relatively slow, then went to a peak, and then it gradually slowed down, and it was 1.0 on the axis, on the vertical axis, where it's just the fraction of the precipitation, and it was a 24-hour time period. And so this was kind of like a typical temporal distribution of rainfall. There are typical runoff patterns as well. And the NRCS method says there's this standard hydrograph shape that it comes to a peak and then it takes a little bit longer to drain back down to zero. And so it's not as crude as the triangular unit hydrograph. You know, when we were making synthetic unit hydrographs with the Snyder method, we said it's a triangle. And even though we maybe made the base leg 1/3 of the storm, and it would 2/3 after the storm to kind of have a slower drainage, still the triangular distribution is less realistic than in the NRCS method, where we're using a unit hydrograph shape that is based on lots of observed storms in a variety of different conditions. And so then all you're trying to do is figure out how big the peak is and how long the storm lasts to then apply that shape. One of the factors that determines how long to make that hydrograph is to look into the accounts of the effects of routing. And the routing means the delay that occurs as the water moves through the basin. And so the sinuosity of the streams, meaning how meandering they are versus how straight they are, is an important basin characteristic. The shape factor, meaning how long and skinny the basin is versus how fat and wide, and the density of the drainage. We talked about some of those general factors, also related to the roughness of the surface, the slope, and so on. So basin characteristics are important for routing, and that routing describes how long it takes until the rainfall produces the peak. And we use all that data for sizing of hydraulic structures, and we haven't yet talked about it, but we will towards the end of the course. We'll begin discussing risk assessment and how to analyze the value of providing flood protection. And so we'll kind of combine some ideas from engineering economy, where we do benefit cost analysis. We'll look at what is the benefit of avoided flooding relative to the cost of providing that protection. So, risk assessment is a really big thing in their, entire master's degree that are focused just on risk assessment in hydrology. And so, unfortunately, we'll have to speed through it in about a week, but it'll be a first exposure of some of the implications of the runoff characteristics. So, like, this is the 10,000-foot view, and we pause now in the course to kind of refresh our understanding of this, because we're kind of at that inflection point between learning all of the theory and the application of the theory through a few more sophisticated hydrograph generating tools like the NRCS method. So here's just another way of conceptually kind of graphing all the ideas together. We have rainfall and we want runoff. And so there's got to be something in between. The model is a way of having the input data that may be a temporally distributed, like a hydrograph. By the way, one of the quiz questions that I didn't give you today, I was going to ask it, but I thought, it's too easy. They'll definitely know it. There's no point asking. What's the difference between a hydrograph and a hydrograph? So the hydrograph would be an illustration of the temporal distribution of rainfall. And the hydrograph is what characterizes the temporal distribution of runoff. So we've got something in between those two. So we start with a hyetograph and we want the hydrograph, so the model connects the dots between these two things. So the factors that are going to go into the NRCS method will be some estimation of the soil that's there, because the soil and the land cover affect the infiltration. Infiltration is one of the biggest differences between rainfall excess and rainfall. We're also going to account for the abstractions. The slope can be in there, the stream characteristics, and then the shape. So all of these factors are taken into account by the model when it translates what the rainfall response looks like to the runoff from the watershed. So it's going to define both the sand and soil characteristics. And the nice thing about both of these is that we can go to data sets that are online, and it takes kind of the burden off of us. Engineering judgment is developed over the course of a career, and sometimes people with a lot of experience can go into the field and just by looking at what types of soils are there and by looking at the type of vegetation, kind of develop an intuitive feel for what the runoff characteristics are going to be like. But they can only maybe apply that to what they can see. And watersheds are sometimes hundreds or thousands of acres. And so a better approach is, what's more data-driven, is to use GIS, where people have gone through and created soil maps and have gone through and with aerial photography identified where are their roads and how much of a watershed is road versus how much of it is maybe residential area, how much of it is commercial property. And so there are maps we can download in a thing called the National Map Viewer. We can get the soil and land use characteristics and kind of automate that analysis, and it takes the burden off of us and it improves the defensibility of a watershed model. And that's another thing that Darren kind of hit on during his description of what they do at DOH is they get sued a lot. I hope nobody here ever gets sued. I haven't been sued yet, although I had one project when I was a real young engineer I thought for sure was going to fail. It was a situation where a client, before they hired us, they knew what size pipe they wanted, and they knew that they wanted it to be plastic. And so, I mean, there really wasn't any wiggle room. They wanted two 42-inch diameter culverts going under a certain roadway, so we said, okay, that's what you get if that's what you want, two 42-inch culverts. But it was a big plastic pipe, so 42 inches is 3.5 feet diameter pipe, so and you'd have to hunch over to get through it, but they were big plastic pipes. They only had about 6 inches of cover from the road to that plastic pipe. So I thought for sure, some truck's going to drive over that and it's just going to collapse. It never collapsed while I worked at that firm. So if it collapsed later, I'm not sure. The point is defensibility, when you're doing engineering design, you have to be able to say, this is why I did it, and this is a good, legitimate reason. And because the client asked for it, wasn't a very strong reason why we did it that way. But if you're basing your watershed model on a standardized, accepted data set of land use and soil type, then that improves the defensibility of your work. And so that's what we're going to ultimately work towards, is not just guessing a C value based on what we look at the watershed and saying, well, maybe it's a C value of 0.6. We'll take the guesswork out of it and we'll calculate something called a curve number in an automated way. And a curve number takes both land use and soil type into account. And it's used in the NRCS method to describe the relationship between runoff and the rainfall excess that goes on top of the surface. So the other thing that the NRCS method is doing is it estimates the distribution, the timing of it. So when these different things kick in, like when the initial abstractions are satisfied, when the runoff will occur, and it translates the flow from the runoff depth using a unit hydrograph. So here's the model. This is a conceptual model, and what it's saying is the first precipitation that you see, we're looking at a hyetograph to begin with. This blocked bar chart, this is when the rainfall occurs. So you can see over here on the vertical axis is saying precipitation rate. There's a certain amount of the precipitation that is satisfying the initial abstraction, and that's what I sub A stands for. It's stored in the catchment before runoff begins. So after the surface wetting occurs, after the building gets wet, after the trees get wet, then there's going to be some amount of the rainfall that satisfies the retention. And so retention, F sub A, is mainly infiltration, but it also includes some local storage. Now this line, this declining curve should look, the shape of that should be familiar from when we were doing like the green amped discussion and the Horton method. It's the declining rate of potential infiltration. And so what it's saying is that there's precipitation, and everything above this declining rate of potential infiltration is rainfall excess. And so here they call that P sub E, precipitation excess. Now the difference between precipitation and rainfall, obviously there are other types of precipitation besides rain. There's sleet, there's hail, there's freezing rain, which hits the surface as ice, there's snow. But everything except for rain gets into the soil and causes runoff at a slower rate than rainfall does. And so rainfall is kind of like the worst case scenario of precipitation. So anything else is going to be less of a problem, with one little asterisk aside that. And that is that if you have snow and it gets warm really fast, then you can have suddenly more water releasing from a watershed than could ever occur during a rainfall event. So just as an example, up in Milwaukee back in the early 90s, they had a really, really snowy winter, and then suddenly a huge heat wave in the spring caused there to be a lot of runoff going into the streams, and all that runoff from agricultural fields took a pathogen into the streams near Milwaukee called Cryptosporidium. And Cryptosporidium is kind of closely related to Giardia. And if anybody here is like an outdoorsman or a camper, maybe you've heard of people getting Giardia before when they go camping and drink from a stream. It's a parasite. So back to Milwaukee, what they had was lots of snow on the ground. It got hot really fast and tons of runoff, so much that the scour and the sediment transport was a lot higher than it usually would be. And so all this Cryptosporidium from basically from cow manure got into the streams, and the water treatment in Milwaukee had no way to deal with it. And about a quarter of the population of Milwaukee got this Cryptosporidium disease, and it makes you really sick for like several weeks. It's pretty nasty. So like that's kind of a famous case study in water quality and drinking water treatment. It made a lot of federal rules enforced by the EPA came out as a result of that incident. So to the discussion of rainfall versus precipitation, usually we're just going to assume that when we're sizing infrastructure, rainfall is the worst case scenario. So sometimes we use those two things interchangeably, precipitation or rainfall. But here, technically, P sub E it stands for precipitation excess. So what we're saying is that the water is going to be in one of three places. The precipitation is going to be the excess, and that's what can run off, because it's the leftover after the initial abstraction and the retention have been satisfied. So this is a mass balance equation. This P equals P sub E plus IA plus F. This is kind of like the continuity equation that you learned back in fluid mechanics, and that is, flow in equals flow out. So here we're saying that if there's runoff from a watershed, it's because of precipitation minus the other things that didn't run off. So this is how the NRCS method kind of conceptually conceives of what's going on inside of the watershed. It's saying that the water's tied up in three places. Now here is an equation that relates those three quantities. It's saying that the ratio of retention to something that we're going to calculate as storage, the potential maximum retention. So this S we can calculate with a related curve number property that the curve number is related to the land use and the soil type, and there are tables of data that says for certain soil types and certain land uses what the curve number is going to be. So I'll show you how to calculate S in just a moment. But the model says that the ratio of those two things is the same thing as the ratio of the runoff to the difference between the precipitation and the initial abstraction. So, in other words, the amount that's actually stored versus the potential storage that could occur. Now, we said that in this conceptual model, the first thing that's satisfied is the initial abstraction. Before there's any runoff, there has to be the initial abstraction. And it turns out that that's really tricky to characterize, because you think about all of the things that we lumped into the initial abstraction, where we were saying there's the evaporation, which we kind of ignore. There is the surface wetting, the wetting of plants, tree leaves, and that varies seasonally, of course. And so what they do is just to approximate the initial abstraction as 20% of the storage. So I'll show you how we can calculate S, and then once you know S, you just, as a starting point, maybe would assume that the initial abstraction is 20% of that. Okay, so I mentioned the continuity equation and referred back to fluid mechanics when we were studying in versus out. And here's in a mass balance, the in should equal out unless there's either some accumulation inside of the control volume or some release. And so if there's a net accumulation, then out will be less than in. We think of it like as a tank. If the tank is filling, then out is going to be lower than in. If the tank is draining, out can be greater than in. And what's inside of that tank? The tank is our watershed. That's the control volume. And how much storage it has is the initial abstraction and the retention. And so these two terms are the accumulation that makes for the difference between the rainfall and the rainfall excess, which is runoff. So here is the formula for storage. And storage is measured in inches in this formula. The tables that you can get in hydrology textbooks and from federal highways or from the USDA, the curve number tables are formatted so that they go up to 100, and then that gives you a storage quantity in inches. Now once you have the storage, then the way that you calculate in the NRCS method, the rainfall excess, P sub E, is with this formula. And if you have the precipitation is greater than the initial abstraction, so remember 0.2S is how we account for the initial abstraction. What we're saying is if you don't have that satisfied, there won't be any runoff. So if the precipitation is less than 20% of the storage, then we assume all of the precipitation is just gobbled up by the initial abstraction. But once you've satisfied the initial abstraction, then this formula will kick in, and it will tell you how much rainfall excess you're going to see depending on the amount of precipitation and the amount of storage that there is. Okay, so let's crunch some numbers here, get a feel for how this equation works. Let's say that we either have a calculator, spit it out, or we go to a table and we get some curve number data for a watershed. Later on we'll learn how to get that curve number data, but for now it's just given. If the watershed curve number is 70, then how much rainfall excess will there be in the first storm, which is a relatively small storm, 0.7 inches. And then for part B, let's look at if the storm is much larger. For a 3.5 inch precipitation, how much rainfall excess is there, and then do the mass balance. You know, in addition to identifying the rainfall excess, identify how much of it went to initial abstraction, how much of it is infiltrated, and so on. So remember, the first thing you have to do is compare precipitation to the initial abstraction. And so for part A, the question is this 0.7 inches of rainfall going to be more than 20% of the storage? Okay, the smaller storm, where it's 0.7 inches, it doesn't accomplish the initial abstractions, as the book would put it. If we look at from the storage, the potential maximum storage based on the land use and soil type that's kind of all rolled up into the curve number, it tells us that the watershed has the potential to hold on to 4.286 inches. Now, that's over a long period of time, by the way. It's not that all of that storage has to be accomplished before there's any runoff. That's just what we're saying the initial abstraction is. So we're saying, as an approximation, 20% of that storage has to be filled before there will be runoff. And so 20% of that 4.286 inches is 0.857 inches. So in this case, if you have 0.7 of an inch of rainfall and 0.857 inches of initial abstraction, there won't be any runoff from that. On the other hand, that other storm, for 3.5 inches, there will be rainfall excess because the precipitation is greater than the initial abstraction. So then the question, now we can start to use this P sub E formula, is how much rainfall excess will there be of that 3.5 inches? So it should be about an inch, 1.008 inches. Of rainfall excess. And so the next part of the example was asked, by the way, before we move on to where is the water, just any question on the example up to this point so far? Okay, so where is the water is asking, let's do this mass balance. Let's find out the rainfall, the abstractions, the storage. Where is it? If we've got 3.5 inches of precipitation and our initial abstraction is 0.857, and here is the precipitation excess, we could just double check the F sub A by substituting in the storage and the rainfall excess that we've already calculated, the precipitation and the initial abstraction. So the F sub A is representing the retention inside of the basin. And so that's mostly infiltration. And so we can get that that's 1.635. And that's the same thing that you would have got if you'd simply subtracted 3.5 minus the initial abstraction minus the precipitation excess. If you'd just done subtraction from that, you'd get 1.635. And so this is just kind of confirming or calculating a different way the difference between the rainfall and the runoff. So this is a model. Remember, a model is just some sort of approximation of reality. And there's essentially 4 moving parts in this model. The moving parts are the precipitation, the initial abstraction, the retention, and the rainfall excess. Any questions before we move on? So this gives us the amounts, but we haven't yet talked about timing. This is just going to tell you for a certain amount of rainfall. You'll notice that this didn't say what was the intensity, and this didn't say what was the duration of the storm. So so far there's no time component to what we've calculated. It's just strictly quantities. So it's not really to a useful state yet. We've already seen all this. Oh, okay, here's a hint for the homework. For problem 3 on your next homework assignment, use the cumulative precipitation up to a certain time, and this formula can be used for the precipitation at that time. The initial abstraction will be a fixed quantity, and the storage is a fixed amount, but what we're saying is that you can find how this applies at many different times. The storage at a certain time is going to be dependent on the precipitation at that time. So just essentially translating this to some precipitation at the time specified in the problem. So refer back to that as you're working on the homework 8, problem 3. Okay, so the two things that we still need to talk about with this NRCS method is, number one, where do the curve numbers come from? And then number two, how do you translate the amounts into rates, into runoff rates? And so essentially, like, what's the time component of when the water's coming out of the watershed? Curve numbers are classified first by characterizing the soil type. And there are so many different discrete soil descriptions that we'll take a look at when we start looking at GIS data from the area around here with the soil mapper that we have access to. You can click on an area, and these soils have names that are sometimes tied to the region of the area, like the era that the sediments were deposited and so on. But what the NRCS method does is defines soils in terms of their infiltration capacity. So group A soils are defined as those that have a minimum infiltration rate between 0.3 and 0.45 inches per hour. Now their maximum infiltration rates can be considerably higher than that, but their minimum infiltration rate is after all of the voids have been filled, after that initial suction pressure has decreased, essentially how much the soil is just draining by gravity. And so type A soils are usually very coarse sands, aggregated silts. I don't want to say that because I'm not sure of the pronunciation. Loess? Any soil nerds want to? All right, we'll all agree on that. So type A soils are essentially heavily granular. On the other end of the spectrum from clays, D soils have essentially no infiltration rate because they are heavily plastic, really heavy clay or saline soils where there's the salt in the soil contributes to the water being bound. What we see most of the time around here are group C soils and occasionally group B. Group A soils are pretty uncommon in Cabell County at least. You can see that group C soils have some clay in it, and there is some infiltration rate, but not a lot. It ranges starting at 0 for the minimum infiltration rate. So the name of the data set that we're after to get this when we go to a GIS database it's called hydrologic soil group. And so the hydrologic soil group will tell us this A through D rating. And then we combine the hydrologic soil group with these land use descriptions. And so you can see, for instance, that in an urban area that has lawns that are in good condition, you would go over here, and here's a description of what they mean by good condition, that the grass is covering 75% or more of the area. So depending on what soil is underneath that grass, the curve number is going to vary. Now, one thing I need to mention is that these curve numbers that you see in this table are for kind of like middle of the road moisture conditions. These are called type 2 curve numbers, where it's not that it's been an extended dry period, and it's not that it's been raining in the immediate days prior to when we're interested in. It's just there's a typical amount of soil moisture, because sometimes we have to convert between these typical soil moisture amounts and the other ends of the extremes. We can get different curve numbers if it's been really wet, or certain curve numbers if it's been really dry. But if you'll notice, the trend is you have a higher curve number with a clay soil. You also have higher curve numbers for lots more paving. So look here at paved with curbs and storm sewers. So paved areas, the curve number is independent of soil type because it's the surface itself that's causing runoff, not the fact that there may be clay under the surface. The vegetated surfaces are more heavily dependent on what soil lays beneath. Here is some curve numbers for undeveloped areas. This comes from your text in Chapter 8. So you can see there are curve numbers for woods. That's what we have around here. I think that the difference between woods and forests is that the woods are usually closer to human development, and it may be roads that are cutting into the wooded areas, because when you put a road in through a wooded area, vines and shrubs grow in the border of that wouldn't have been there if it was uninterrupted like forest land. And so there is a technical definition that differs between the woods and the forest lands, and you'll notice that woods usually have a slightly higher curve number than forest land would. So according to this essay, what are the two factors that almost condemns the United States to, how does it put it here, almost condemns it to, well, anyways, the United States is going to be prosperous because of what two primary factors? Transportation and the agricultural regions that overlie each other. So I guess together those are the geographic benefits. So there's a lot of arable land. You know, the Midwest is suitable for farming, and then you've got this network of navigable rivers where, you know, a farmer, if we look at a map, I guess if we go Mississippi, then that, okay, this is a good one. So this is showing the watersheds that contribute to the Mississippi River, and of course there's also the Missouri River that drains even more of it. But farmers as far north as Minnesota, South Dakota are able to put their agricultural products onto barges, and ship traffic can go down the Mississippi River. And as the article was saying, there are a lot of protected ports in the United States, and that's not always the case. A lot of countries have ports that are really strongly affected by the weather, or they have to spend huge amounts of money to excavate inland so that they can have protected bays. But the United States has some of the best ports in the world just naturally, ports and harbors. And then the other thing that's really important about it is not just that it's flat land and that it's got rivers going through it, but also that, you know, the soil characteristics and the weather characteristics make it suitable for crops like wheat, soybeans, corn. You know, there are a lot of places in the world that have rivers, but like in the case of Russia, they're flowing the wrong direction. If we take a quick look at the rivers in Russia, Russia has even more land than the United States, and a lot of it could be potentially useful for agriculture. But the problem is that the Russian rivers flow to the north, and so that means that during the winter months, those rivers completely freeze over, and so it's not navigable through the entire year like the United States is. You know, although in some rare occasions there may be a bit of ice on the Ohio River, it's usually just for a few days. But there's a series, I think 5 or 6 large rivers in Russia, and they all flow to the north, and that makes it so that they have to, if they want to use these middle areas for agriculture, then they have to spend a lot more money putting in rail networks or roads, and so the cost of transportation for either rail or highway traffic is a lot higher than, like on a per ton basis. You can move crops around on barges for very, very little. It's extremely cheap. So it's kind of interesting that it says, like on the back side of the paper, it was saying that when you've got get the cake for free, you can afford some pretty nice icing. And the highway systems that the United States built in the 1950s, it was able to make the interstate highway investments at the same time that most of Europe was just kind of dragging itself out of the recovery from World War II, and a lot of other countries just hadn't gotten enough capital together because they didn't have these same structural advantages. So I'm wondering, are there other things that stood out to you as you were reading this as important factors for America's economic growth? Yeah?
So as an investor, would it be a better choice to put in less amount to your retirement fund until it tanks, then put in the full amount because you're going to get the greatest interval amount?
Yeah, so if you know when it's going to tank, if you can time the market, then absolutely. But everyone always talks about the folly of timing the market. So I mentioned that financial crisis. And this kind of shows cycles, right? Cycle, bust, boom and bust. And this is that financial crisis that this was written in. It was like late 2007, early 2008 that things started looking a little bit shaky. And I first got to Marshall in January 2009, and like everyone was walking around shell-shocked at that time. It looked like banks could fail. I felt really lucky to get a loan for my house because there was a big squeeze on lending. People tightened up. Banks were less likely to loan because the credit market was kind of in trouble. So your question, is it better to buy low? Absolutely. But it's only in retrospect that you know when low is and when high is. Like the people, if we just go to some of the specific numbers here, at the peak of that pre-financial crisis, this is one particular stock index. This is called the S&P 500 index. It's a accumulation of 500 of the largest companies in the United States. And so this index was about $150 a share. And so maybe it looked like it had tanked when it was down to 133. The investors thinking, well, it's down already 10%. That's a huge loss. But then it did get as low as $77 a share. But if you could buy in then and now, it's up in the 300 range approximately, approaching 300, then yeah, that's pretty sweet. But I think speaking from my own personal experience, the least maddening way to invest is just to have the same amount go in every month. Just make it automatic enrollment, put in as much as you can afford to, and then just try not to look at it, because sometimes it'll go up, sometimes it'll go down, and it'll just drive you nuts if you fixate on it. Yeah. So one of the things that stood out to me here is about like the lack of competition in the Western Hemisphere. Like if you look up and down, both North America, Central America, South America, there aren't a lot of places that have these same advantages that the United States does. There are a handful of places that are nice agricultural regions. Like Chile has good arable land. Brazil and Argentina have like emerging agricultural sectors, but they don't have this interconnected network of rivers. Another kind of interesting thing is that geography also allows the United States to not have to keep a standing army that's very large. Like imagine how different it would be if we had China on one of our borders, or Russia. I mean, they're so far away that it kind of gives the country a little bit of breathing room, and then as it points out here, it ties up a lot of the capital. It frees up a lot of capital and people from having to work in the army or having to work in government subsidized and organized transportation, now that can go into the free market, which is a lot inherently more more efficient. So it's, we talk a lot this semester about how water is a danger, that we have to get out of here, that we have to treat it as a pollutant or a threat to infrastructure. But this, I think, is a good reminder that water is also a resource. And, we already know that since we drink water and it's used for the production of crops, but just water as a means of transportation, whether it's the rivers or the intercoastal waterways on the East Coast, it really kind of shaped what kind of country America is. America probably wouldn't have been successful as laissez-faire capitalism if it didn't have these same structural advantages. If you travel through Europe, you see, the European countries really have to organize to make it work. They have better rail networks than we do. They have like lots of locks and dams, and those are huge investments, and taxes are higher over there because they didn't get their cake for free like we did in this country. So I think you should hold on to this. Maybe I'll throw in a question or two on our final exam related to the ideas in here. It's an article that I've held on to, obviously, for 10 years nearly now. I think it's a good one. But now let's talk about the NRCS method. So last time we took a look at these curve number tables. Remind me what the A through D classifications are related to. A through D across the top. It was soil types. Yeah, so on the spectrum of A through D, one of those soil type, at one side you have soils with a high hydraulic conductivity, and on the other you have soils with a low hydraulic conductivity. Do you remember which is which?
Like the bentonite clay.
D is clays, plastic soils, saline soils, where there's going to be a low hydraulic conductivity. And so if you look at these numbers, across one of the rows, so if we just look at lawns that are on clay soils are going to have a curve number of 80. And what that means is that there's going to be more runoff than infiltration. But then at the other end of the spectrum, these Class A soils are the ones that are sandy and have relatively high hydraulic conductivity. And so Class A soils have lower curve numbers. So a lower curve number means there's going to be more storage and therefore less runoff. If we just go back to the NRCS equation, let's take a quick second look at that. Okay, so here's the NRCS equation, and a big part of that is the storage. And so storage comes from curve number. And if a curve number is big, then what that means is storage is going to be smaller. And so there would be more precipitation excess. But if the curve number is relatively low, that means that the storage and the lion's share of storage is the infiltration, then there would be less precipitation excess. So now back to these tables. It's a combination of land use and soil type. And when we get into modeling on the computer, we're going to use GIS data to tell us in a certain watershed how much residential area do we have, how much streets and roads do we have, how much cultivated agricultural land do we have. And that data is out there. It's published by the federal government. And the same thing, we'll have databases of soil type. So these curve number tables that we were looking at are for typical moisture conditions, just kind of not a particularly dry stretch, not a particularly wet stretch. But we need to sometimes be able to convert from those typical moisture conditions to the other ends of the extremes. So what these baseline tables are for curve numbers in type 2 conditions. And type 2 is just the antecedent moisture group that's in the middle. And so what that means is that during the dormant season, for instance now, when the crops aren't growing, we'd expect that in 5 days, excuse me, the rainfall totals during 5 days would be from 1/2 inch to 1.1 inches. And so right now, it hasn't rained here in Huntington for, I don't know, a few days. I don't remember when the last time it rained. Maybe, was it Saturday? I was out at Bridge Day and it sprinkled on us a little bit. I don't know what it did here. But probably right now, since it hasn't rained here in Huntington for the last few days, in the last 5 days, our total rainfall is less than 0.5 inches. And so that means that the soil conditions are antecedent moisture condition 1 right now. And so what that means is we'd need to, if we're going to do an NRCS analysis, and if we wanted to know how is the watershed going to behave, we couldn't just use these curve number tables and put it into the NRCS method, because right now the soil is a bit drier than these curve number tables are derived for. So here are the formulas. These are just empirical equations that make some adjustment based on observation in the past, and there's nothing fundamental about them. And you know, the conditions really can be different than is predicted here. And you look, it's a range, and so you know, for instance, antecedent moisture condition 3 is when there's been over 1.1 inches. So it could be 1.11 or it could be 5 inches, and it's going to treat either of those as the same. And so there's limitations to this, but it's a correction that's better than not making any correction. So just to get a feel for these conversions and to show you how widely it causes the curve numbers to differ, let's take a look at, for residential quarter-acre lot on Class B soil, that normally would have a curve number of 75. So let's just go to the table and make sure that we see how we'd get that. So residential quarter-acre lot, Class B soil. So let's go here. Residential is the land covering, and so that's going to be a mix of some roof area, probably an asphalt driveway, a lawn. And so what they're doing is they're saying typically people have a mix of impervious and pervious surfaces in residential area. And the quarter-acre lot is significant because when someone has a 2-acre lot, they're going to have relatively more yard to roof. You know, that ratio would be more favorable towards the impervious compared to the building. So what you'll notice is that as the lot size increases, the curve number is going lower. And that makes sense to us because it's just a reflection of there being more vegetated space as the lot size gets bigger. But in the example that we're going to do, it says quarter-acre lot and then Class B soil. So we have the intersection of quarter-acre row, Class B, so curve number 75. Now that's only going to be valid, this 75, is if there is, in the past 5 days, between 0.5 and 1.1 inches of rainfall during the dormant season, or 1.4 to 2.1 in the growing season. But we want to find out, what if there's been no rain in the past 5 days? So in other words, find the curve number under type 1 conditions using this formula. And then what would be the curve number if in July, meaning during the growing season, it had rained 3 inches in the last 5 days. So then that puts us into antecedent moisture condition group 3. So find curve number under condition 1 and curve number under condition 3. And we'll look at the range that gives us. Okay, so what we see is that if the curve number is a 75 under this middle range moisture conditions, then under the type 1 conditions, which means a little drier than average, then it could be as low as 56. Under the wet conditions, it could be as high as 87. So from 56 to 87. Now let's look at what that means. If we go back to the curve number table, okay, we were starting in this example with a residential land, quarter-acre lots on type B soil. 75 is the middle, but it could go from 56 to 87. So try and find something that's similar to 56. If we go to this table, 56 maybe would be like a 1/3 acre lot on type A soil, which is pretty different conditions. Or if we go down here to the croplands, something in the 50s. All right, forest. So a type B soil for forest land on good condition, meaning like the density of the vegetation. It could transform the effect of a residential area, which has quite a lot of impervious area. It could turn it into something that is entirely vegetated, the hydraulic effect of that, if the soil is going to absorb more than average moisture. But then at the other end of the spectrum, taking it to 87, then that's almost like we had taken this grassy area and now it's going to have the same absorptive ability as like gravel streets. And gravel streets don't absorb as well as vegetated areas. And so it's a pretty big spectrum. And the other way to see that is if we calculate the storage, the S, based on these curve numbers. And so, for example, with the curve number Cn of 87, then S, where S is 1,000 divided by the curve number minus 10, the storage for 87 is 1.494 inches of storage, and for Cn of 56, then the soil has the potential, the maximum storage potential of 7.86 inches. Now, remember, that doesn't mean that there has to be this much rainfall before there's any rainfall excess. It's not quite like that, but this represents the maximum storage capacity of the soil. And so that, I think, illustrates the effect even more. So the effect of a curve number change isn't linear, is my point. Where we started at 75, if conditions are really dry, then the soil is going to absorb quite a lot more water than if it's been very wet in the past few days. And so the take-home message that you need to take from this is that if you're doing a hydraulic modeling and you want to account for the worst-case scenarios, it's not just analyzing what the watershed will look like when the area is fully built out. And that's an important part of it. And that's a big part of why here in Huntington we have so much flooding, is that they built a lot of the sewers before they had any idea how populated the city was going to be. A lot of neighborhoods that now contribute runoff weren't accounted for in the sizing of those pipes. And so it is important to think, well, I need to put in this infrastructure to handle the demand that there's going to be a long time in the future. So that's definitely part of it. But then also the range of conditions. And so, looking at the range of maximum precipitation for the storm in question, but then also the antecedent, so the prior storms, because that's going to have a huge effect on how the watershed behaves.
So this storage term,
Mm-hmm.
is that, so for a low curve number, you're going to have a high storage.
Mm-hmm.
Is that infiltration storage?
Most of it, yeah.
Okay.
Mm-hmm.
Not
If you go,
storage on.
if we go to the precipitation excess formula, it's mostly infiltration, but because our initial abstraction is based on storage, it's also saying that if it's rained recently, then you're going to need less surface wetting before the water starts to flow overland. So the leaves are already wet. The puddle, like the local depressions may already have some water in them. So just everything, all of the abstractions that have to be satisfied before there's runoff, they're more likely to already be close to satisfied when you've had rainy conditions in the previous 5 days. Yeah, so it's mostly infiltration. And by the way, on the quiz, I tried to be generous on it, but on the description between rainfall and rainfall excess, it's not just infiltration that makes them different. Infiltration is the biggest of the factors that cause them to differ, but then there's also surface wetting, interception, local depression storage, and so those are other abstractions that also account for the difference between the two. Infiltration is the most important, but it's not the only one. So are there other questions about antecedent moisture condition? Okay, now luckily we can just come up with a simple weighted average to find out a composite curve number for a basin. It is that simple in a field where not everything can be just area weighted. The composite curve number can. And what I mean by that is if you have a watershed that has different things in it, like if you have a watershed that has some residential areas, some agricultural areas, maybe a commercial zone and so on, and you want to find the overall curve number for that basin, then all you need to do is just multiply the fraction of the watershed by the curve number in question, and then you can come up with an average CN. And so let's take a crack at that. Come up with a weighted curve number for this watershed, and then let's again go through the process of calculating the storage and then the precipitation excess when we have a defined storm depth of 6 inches. So on this, the first step will be to find the average curve number. And it's not a simple average. We're not just adding them together and dividing by 4. But what you should do instead is, based on this land use percentage, where it says 40%, so just multiply 0.4 times the 83 curve number, and then so on and so forth, add them all together. Okay, so the weighted average for this watershed, the curve number should be 86 when we multiply the percent of the area that has each one of those curve numbers. So 86 is the weighted average, so then the average storage capacity inside the watershed is 1.628 inches. And if we have a 6-inch storm, then that means of the 6 inches, 4.41 is going to be rainfall excess. And that's quite a large storm. You remember I told you about the situation they had in Milwaukee back in the early 90s, cryptosporidium, because it got warm really quickly and all the snow melted. They're having a similar thing right now in Austin, Texas, although it's not related to snowfall. It's just that they had a lot of rain all at once, and the river is extremely turbid. Like the suspended soil particles in the water are so high that they can't get them out at the treatment plant. So they're having to, they issued a boil water advisory down in Austin because they know what happens when there's a lot of turbidity. Then the bacteria get through because like the pathogens can hide inside those little soil particles, and they don't get access to the chlorine to inactivate them. So it's kind of interesting. I saw that in the news the same day that we talked about it on Tuesday, that they're having boil water widespread, and it's going to be a long time too, because it's going to be a while before the river levels go down and the scour subsides. So it's a direct relationship between some storm event and then the treatment processes that are required to make the water potable. So this is probably a big enough stream event. 4.41 inches of rainfall excess is going to be so much that there's going to be a lot of flooding and scour. And so just kind of understanding the consequences of hydrologic events like this, I think, is pretty important. Any questions about this example? Now, in this example that we just worked through, we didn't give any attention to where in the watershed different land areas were. And we can do that, and sometimes it makes a difference. This was just kind of like saying we have these isolated areas where there are certain spots that have a pretty high curve number and certain spots with a relatively low curve number, but we're mixing them all together. Sometimes we need to pay attention to the relative position of pervious and impervious areas in a watershed. So take a moment to consider the figure on the left. What this is saying is that we have a 10-acre watershed, just as an illustration, with two distinct land uses. We've got one land use that is pervious area, so that could be grass or other vegetation. And then we have downstream of that, see from this arrow you can see the direction of water movement towards the outlet. But downstream of the pervious area is some impervious surface, so meaning asphalt, concrete, or it could be buildings with roof area. So in this illustration it's saying, let's just take as an example pavement that has a curve number of 98 down here in the impervious area, and then up top let's assume that it's grass with a curve number of 60. So there is a more sophisticated way of determining the effective curve number than a weighted average, because this pervious surface can, if the positions are reversed, allow for some additional infiltration that can't occur right now. And so what I mean right now is the impervious area is directly connected to the outlet. And the effect of that is different than if it's not directly connected to the outlet. If we'll, in the next slide, look at what if it's reversed. What if the impervious is up top? So in this first example, we could either calculate the weighted average or we could use this nomograph. And so let's just see if we can figure out how to use this nomograph. We have a total of 30% that's impervious, and it's directly connected to the outlet. So if 3 out of 10 acres total is impervious, then what we can do is we can follow here on the x-axis, we find the 30%, and then we would go up to the line that represents the curve number of the pervious area. And so each one of these curves represents what is the curve number of the part that's pervious, and in our case it's 60. So I'll start here at the 30% connected impervious and go up until I reach the 60 curve, and then over to the left from there intersect the vertical axis, and it's 72. So that's how you do it for if it is the impervious area is connected, because there isn't any special absorptive effect that occurs in this configuration. But now consider if the situation is reversed. It's because it's 3 acres of the impervious, and the total, meaning area 1 and area 2 together, is 10, and so it's just 3 out of 10, so 30%. Right. Yep. Did you have a question?
Yeah. Why is it that we use the pervious number when you're you're using the connected impervious area, but why are we using the pervious number?
This is kind of a graphical way of coming up with the area weighted average, similar to what we just did. And so it's assuming, in this table, it's assuming that your impervious area is pretty close to 100 for the curve number. So it needs to know, for like the combined overall weighted curve number, it needs to know what is this, this grass. In our case, it's grass. If it's going to come up with a weighted average, it already knows that the impervious part is about 100. And so it's asking, so what's the curve number of the part that isn't pervious? So we have to give it some input of, if we're combining two things together. Let me put it on the whiteboard. I think that'll probably eliminate any uncertainty. So we've got the average curve number is going to be the combined effect of the pervious and impervious. And each one of these, the pervious is, we need to know the area times curve number of the pervious, and then the impervious is going to be its relative area times the curve number of the impervious. So this table combines all this together. It's saying the impervious, let's assume about 100 for the impervious curve number. And so we have to define these three other things. We have to define the relative areas of the pervious and the impervious, and then also the curve number of the pervious. And so the area thing is defined by, we're saying it's a mix of either pervious and impervious. And so the 30% is when we say how much of each we've got. And then these pervious curves is where we define what is the curve number of the part that isn't asphalt. So this table is essentially just a weighted average. There's nothing special going on in this one, but in this one it is kind of special because think about the runoff from this asphalt is not going straight to the outlet. Before it gets to the outlet, it's going to flow through this portion of the watershed that allows for infiltration. And so the rain that falls on the pervious surface, a portion of that is going to be infiltrated, but even the rain that fell on the impervious area, it has a potential for some infiltration as it flows over the pervious area. So whereas we calculated a curve number of 72 if we had 3 acres of pavement that was directly connected, if that same area, if the same 3 acres is up top, we'll go through the process, but what we're going to see is that the curve number is lower because some of the runoff ends up infiltrating as the water flows over the pervious area. So the way that we go through this is, first of all, we have to start with the ratio of unconnected to the total impervious. And so this impervious surface right now is completely unconnected to the outlet. It's not directly connected. Like it was here, it was directly connected. So over here on the vertical axis on the right, we have 100% of the impervious is unconnected. So you'll see here this ratio where it says unconnected impervious to total impervious. So we have 3 acres of impervious surface and all of it is unconnected. So we're going to use this 1.0 curve. And then the total for the entire watershed, 3 out of 10 is impervious, and so 30%. So we go over at the intersection of 30% and 1.0. We start moving to the left until we reach the curve number that represents our pervious, our pervious surface, the grass curve number of 60. So we're going over here until it intersects with this right here, the curve number of our grassy area, and then we bring it down to the intercept on the horizontal axis, and it's in the range of 65. So again, let's just go sideways over until we reach 60, and then down. So between 60 and 70. So the effect that this is trying to account for is the fact that the sheet flow that's coming off of this parking lot, that sheet flow, some of the water will get into the soil as it flows over the grass. Not all of it, but certainly more than in this case, because in this case, all of the sheet flow from the parking lot just went straight to the catch basin. It's the same idea when we said that it's a best management practice for people to disconnect their roof drain from a combined sewer. You know, here in Huntington, some people have the drain from their roof going into the sewer. And then when it rains really hard, that kind of contributes to the risk of there being sewage discharge into Four Pole Creek and Ritter Park. But if people disconnect their roof drains, then that means that the water has to flow over their front yard before it gets into the catch basin. So it kind of reduces the amount of rainfall that ends up stressing out the combined sewer. So this is a similar effect. In this case, we had 100% of it was unconnected. Just to round out the example with one more look, now we have some of the asphalt is directly connected. Some of the asphalt is unconnected. So it's half and half. And that's where, on this right curve, where it's saying the ratio of unconnected to total for the impervious. So we have 3 acres of total impervious area, and 1.5 of it is unconnected. So that means 1.5 divided by 3, this 0.5 curve is what we would use. And our total impervious area is 30% because it's still 3 acres out of 10. So we're using this 0.5 curve and 30%. So we go over until it intercepts the 60, which is the curve number of our pervious area. And then we take it down from there to the intersection of the horizontal axis. So the curve number effectively would be 68 for this. So it's kind of a mix of direct connected and disconnected impervious area. Now I think I've said impervious enough times for the day. Any questions about this concept?